complete idea of how to do inverse kinematics for a 6 degree of freedom manipulator, because most of the 2 degrees of or 3 degrees of freedom do not control the orientation, they only control the position of the manipulator. Okay, so for the, I'm going to email you the exact lab case where we'll have a DH table. I think you will work it out before you come to class so we can check the solutions that you have derived by a MATLAB simulation. However, for the purposes of the midterm, right, we'll stop till decoupling, okay? This is where we'll have till decoupling, and after that, whatever we continue from now on will be a part of the other, okay? So inverse kinematics, which includes decoupling. So for your midterm, you'll have the basics of rotations, R3 by 3, right? H4 by 4, okay? Forward kinematics, okay? DH notation, and inverse kinematics. Okay, obviously, inverse kinematics includes 3DOF, which is simple solving it geometrically, and 6DOF, which is decoupling. All right. So, simple rotation matrices are 3 by 3, homogeneous matrices 4 by 4, forward kinematics, finding XYZ given thetas, doing a DH notation, we have done a lot of examples, and doing inverse kinematics. We have to do a few problems. We'll do a few numerical problems in inverse kinematics.
And when's the...
I'm going to set up a date and I'll email it. Okay. So it's going to be a 2-part exam, which is basically you'll give a exam in class, and because there is not so much multiplication that you can sit and do in class, I'm going to give you a simulation problem, a part of it which you'll solve in class, the other part you'll take it home and you'll simulate it in MATLAB, okay, to make sure. So by the time you simulate, you'll already know whether you did well in the exam or not, right? Because if you don't get the same answers, I think you'll help me grade your own paper, right? So that's how we'll do it. Okay, so till this point, it is basically understanding how a manipulator behaves when it is static. But obviously, we are not talking about manipulators.
So, one last question regarding the midterm
please.
exam. Because we have lots of matrices, we need to, memorize them, or you
Okay,
provide...
I'll tell you, there is only 2 things that you have to basically memorize. I expect you to remember the R matrices, okay, R3 by 3. I expect you to remember this, right? Which is R, X theta, Y theta, or Z theta, or whatever. Other than this, there is nothing to remember. The only AI, I'll give it to you. Okay, I don't expect you to remember the AI matrix. Okay, AI, I'll give it to you. But that's the only thing you need to remember. I don't think there's anything else that you need to remember. DH table, you have to know the rules. Write the DH table. So if at all I'm using AI in any of the questions, I'll give you what the AI matrix is, so you can actually substitute the values and you can compute that. Okay, so that it leaves us with simulating a few things. Let's talk about motion, right? Manipulator motion. So how do you study manipulator motion? So let's take velocity of the atom. Okay. We'll talk about motion of a manipulator. We'll start with a simple, as always, we'll start with a simple 2 degree of freedom manipulator. So we know that X for a 2DOF planar manipulator X is nothing but A1 cos theta 1 plus A2 cos theta. Okay, y will be equal to A1 all right. So we have this manipulator here, and it could be moving in this direction or in this direction, right? How do you create motion? We create motion by having θ1 and θ2 move, right? So if I want a certain velocity for the end effector, I have to have a certain velocity of θ1, θ2. The only way I can control the motion of this is by controlling θ1 and θ2. So there has to be a relation between θ1 and θ2, okay, and the velocity of the end effector, which is, let's call this as Vx and Vy. Okay. Let me quickly, let me do one thing. Let me give you, for those of you who are following this, let me give you the chapter numbers. So for the, let me interrupt, I'm sorry. This will be for the midterm, just for the case that you need chapter numbers, 1, 2, 3. Okay. 1 is basically introduction, 2 is your matrices and everything, 3 is forward and inverse kinematics. Okay. 1, 2, and 3. I think DH table is also a part of 3. So this is DH, forward kinematics and inverse kinematics. This is your R3 by 3 and H4 by 4. And this is your intro. Okay, it's basically the definitions and everything. I think, yeah.
Professor, will there be any theoretical question?
What is the theoretical question? This is not social sciences, right? Everything is going to be problem solving, right? It's only going to be problem solving and simulating your own results in MATLAB so that you can double check your answers, that's it. In the class, for the class part, I'm going to ask you like very short questions. Some of them will be short, some of them will be a longer problem where you have to solve for some cases. Or in some cases where we have derived for something, I'll give you numerical examples. Okay. For example, if I give you a structure and I give you px comma y comma z. So if I give you a manipulator structure, px comma y comma z, you'll find θ1, θ2, d3, or whatever. Right? We have derived it, but you'll put numerical values to that and you'll do those. So make sure you have your calculator. Most of it is only going to be conceptual, which is basically understanding what we have done. I just want to make sure that I have given you, I'm not missing anything before we move on. Okay, so I think most of it is here. If I see something, I'll surely email you, or before that, I'm obviously gonna see you in class, so we can obviously do that. Okay, so what we want to do is we want to establish a relation between Vx, Vy, and theta dot and θ2 dot. The reason is because, let's say I have a desired velocity. I need to have the desired joint velocity to generate this, right? So forward velocity is is given theta 1 dot and theta 2 dot, find Vx and Vy. In this case, obviously, right? So you know the joint acceleration or joint, I'm sorry, not joint velocity, this is your joint velocity. We need to find end effector velocity. Okay. Now the inverse problem is obviously just like we did in kinematics. The inverse velocity is given Vx, Vy, find the required theta 1 dot and theta 2 dot. So I want to generate this velocity. What should be my joint velocities? I want to, in this case, I have the joint velocity. What will be my end effector velocity? Okay. So this we want to establish a relation. So if I differentiate these, so let's say that I have x, which is a1 cos theta 1, a2 cos theta 1, 2, y is a1 sin theta 1, a theta 2, right? So if I differentiate these two relations, Vx will be equal to dx by dt with respect to time. So here I'll get minus a1 sin theta 1 d theta 1 by dt minus a2 sin theta, this will be sin theta 1 2 times d theta 1 dt. Okay. So I can write this as Vx will be equal to a1 sin theta 1 d theta 1. We'll call this as d theta 1. Same way we can write a relation here. Vy will be equal to, in this case, so if you take theta 1, theta 2 common, so I can write Vx will be equal to okay. Now we can set it up like this. So this will be a relation between the velocities, end effector velocity, and the joint velocity. This is your joint velocity. And this is your end effector velocity. This matrix here, which provides a relation between the velocity, this end effector velocity and joint velocity, is called a Jacobian. A Jacobian matrix is basically represented as J of Q. Okay? A Jacobian matrix is represented as J of Q. It provides a relation, a mapping between end effector velocities and joint velocities. So I can write this as V is equals to J of Q times theta dot, or Q dot, because Q is the joint vector divided as Q dot. Okay, so V will be equal to J of Q times Q dot. So this matrix, in this case, we have derived it, we differentiated this, but if you look at forward kinematics equations for 6 degree, 7 degree of freedom manipulator, it's not as simple as deriving it in 2 steps, because thetas will go on to theta 5, theta 6, so you cannot do that. There has to be a different method to calculate a Jacobian, and this is what we will investigate, how to find the Jacobian matrix for different manipulators. In a simple case, we can just derive it like this, as we did with forward kinematics. For the 2 degree of freedom manipulator, we could tell this is A1 cos theta 1 plus A2 cos theta 1, 2, and we can do this. But for larger manipulators, we found out it's much simpler to do A1, A2, A3, and so on till AN, and then you take the last 3 values from the H0n matrix or T0n matrix, and you can find XYZ. That's much simpler than doing it geometrically. Same thing here. If we develop a technique to find JQ in such a way that we don't have to differentiate the forward kinematics equations, it will be very simple. And this we'll need to use the DH table for it to find how to find out the J. So we'll talk more about this, but in the next few classes, we'll try to simulate the decoupling and everything so that you have a better grasp of when you see the midterm paper. So we'll try to do most of this after the fact that we have finished simulating the decoupling and inverse kinematics of 6D Earth. Okay, let's stop here. You have an assignment to do a 6 degree of freedom DH on Thursday. Please bring that with you so we can simulate it.